If you're a little intimidated by getting into FPGA because you think you don't know enough, then don't be. Watch through this video. In about 20 minutes, you'll have what you need in order to get started, and also watch the rest of my evolving series about hobbyist FPGA programming. Keep watching. So what we're doing here is to build an electrical machine that will fulfill tasks for us, and we're going to do that with a lot of logical gates connected together. What are logical gates? Those are conceptual beings that are based on physical beings like transistors and resistors connected together in a way that everything is designed such that the system will talk in the language of zeros and ones. And how do we do that? So if you look at the voltage graph, we're going to pick an area and call it R1 and another area and call it R0, and we're going to try to keep ourselves out of anything else, or at least to be there for as short time as we possibly can during transitions. And we do that for practicality reasons. It's simply easier to build computers this way. So we are going to see logical gates now, but keep in mind that those entities are actually built upon physical beings like transistors and resistors that are eventually analog devices. So if we take a look at the 2-input and logical gate, it takes 2 inputs. Each one is either 1 or 0, but as you can see, we are using, of course, voltages as our inputs. But the system is built in a way that those voltages will be, in the vast majority of the time, either our 1 or our 0, as well as our result. So eventually, during our design, we will allow ourselves to think of a chip as a bunch of logical gates as opposed to a bunch of analog elements, despite the fact that it is of course built on analog devices. The circuitry will be built in a way that we will be able to work in a higher level of abstraction, which is the logical gates. We have been talking about logical gates. Let's see what they are. So we have the basic 3 logical gates. We have the AND gate, in which only if both inputs are 1, the output is also 1. This is just an example. The OR gate, where the output is 1 if either of the inputs is 1. And the NOT gate that reverts whatever is in the input. So if you have an input of 1, the output is 0 and vice versa. And each of the gates can be described with a truth table. Let's take the AND gate as an example. I have enumerated all possible options here, and you can see that only when the 2 inputs are 1, the output is 1. And this can be described in a truth table. The truth table enumerates all the options for all the inputs and all the outputs. And these are the tables for all 3 basic gates. With just those gates, we're going to jump ahead and fulfill the first task with hardware, with logical gates. So if we have 2 bits, 1 and 1, for example, the summary is 0 and we have 1 carry. We can enumerate all the options. 0 and 0 is 0 without a carry. 1 and 0 or 0 with 1 both have no carry, but the result is 1. What we just did is called a half adder. A half adder has 2 bits as input. It has 1 output that is the summary and 1 output which is the carry. And this is the truth table for a half adder, and you can see that it matches exactly what we did on the whiteboard. This is a canonical equation that expresses the same table. Multiplication is actually an AND, an addition is an OR, and a tag is a NOT. So for example here, the carry equals 1 only if A is 1 and B is 1. Let's take a quick look at the notation. A times B is actually A and B, and on the right you have the gate that symbolizes that. A plus B is A or B, and you have the gate on the right. And A tag, or sometimes A bar, is a not A, and you have the gate on the right. And this is the gate representation of the truth table and the equations. So you see, we have a task, we convert it to a truth table, and then we achieve eventually a gate level implementation. And we have to take into account propagation delay, because those logical gates are built on physical components, and since electricity doesn't flow at an infinite speed, it means that it will take time for the answer to form. And more importantly here, you can see that the path from A and B to C has less logical gates than the path from A and B to S, meaning that the time that it will take for the answer to form will be shorter on C than it is on S. Let's elaborate just a little bit about propagation delay. If we have this simple arrangement, then the result is 1 because A is 0 and therefore not A is 1, and this OR gate has one input of 1, which is sufficient to have 1 as the result. In a perfect world, if A is transitioning from 0 to 1, the result is still 1 because on the end we have now 1 and 1, and the result on that is 1. And now we have this 1 here on the OR gate and again 1. So in such a perfect world, the result will just stay 1 all this time. Now let's see what happens in the real world, and let's assume those gates have those propagation delay times in microseconds, and those are made up times. It's just for the sake of the example. We begin again with a system where A is 0 and B is 1, and after a while the system has been stabilized on the correct answer, which is 1. Now we are changing A from 0 to 1, but now the answer at the end of the OR gate is not immediately changing because there are propagation delays on the way. After 1 microsecond, the NOT gate has changed from 1 to 0, and after an additional microsecond, two things happen. First, the AND gate has responded to the new input, and now the answer on the AND gate is 1. But also the OR gate has responded to the new input, and now the answer there is 0. Note that the new value from the AND gate is yet to propagate through the OR gate at this point. After an additional microsecond, this new input propagates through the OR gate, and now the OR gate is back to 1. And then the system is stable again on the correct answer. This phenomena right here is called a glitch, and we will see later in this video how we deal with glitches. But this demonstrates how a combination of logical gates takes time to settle on the correct answer. Alright, so now we want to extend our logic from just one bit to multiple bit adder. So if we look at a long addition, we move from the least significant bit to the most significant bit, and we do an addition. So 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 2. So 0 here and carry over to here, and 1 plus 1 plus 1 is 3. So 1 here and the carry of 1. In order to implement that in logic, we're going to use a full adder. A full adder is very similar to half adder, except it has another input, which is carry in from a previous stage. So we have three inputs, A, B, and C in, and we have two outputs, which is the summary and the carry out. And on the right, you can see the truth table that enumerates all the options for those inputs and all the outputs. And the equations that express this table is those that beneath it, and you can see here a new sign, which is the exclusive OR. And exclusive OR is 1 only if either of the inputs are 1, but not if both. You might ask yourself, how did I get from this table to those equations? The answer is you can do the hard work, or you can use something called Carnot maps that helps optimizing those tables into those equations. And with your permissions, I'll skip Carnot maps now. And if you tell me in the comments that you want me to go over it, I can add another video about it. But you will seldomly use it probably if you're doing digital with description languages that we will see in future videos. If we translate those equations to logic, then this is what we get. So now we can chain 4 of those full adders to have a 4-bit adder. And you can see that on the bottom I've put a half adder, or you can alternatively put a full adder and have a 0 carry in for the least significant bit adder. And you can see that the result goes from the least significant bit to the next one and all the way to the most significant bit, and eventually there is a carry out at the end, which is just 1 bit. And this is called a 4-bit ripple carry adder, and this is because the answer kind of propagates through it. And as you can imagine, if you look at it like that, it might be a little bit easier from left to right. There is a lot of propagation delay here. So this is not a very efficient way to do an adder, but it's simple and it works. Let's look at another entity that is very commonly used, which is the multiplexer, or MUX in short. It has two inputs, A and B. In this example, it's just one bit each. And there is another bit called select that will select which of either A and B will go throughout. And you may ask yourself why we need such an entity. And the answer is, in hardware, remember, everything has to be connected. It's not software in which you can choose what goes where. In hardware, if you need an option for something to go somewhere, you need to connect it physically. So we will see very shortly how this is being used. On the right, you can see the truth table for MUX. And it's very simple to convert it to an equation. Basically, S is selecting, for example, if you look at the left-hand term, when S is 0, then S tag is 1, and this entire term here equals A, while this entire term here equals 0, and vice versa, where S equals 1. You might have noticed we have moved from just gate level to something we can maybe call a block level, okay, in which we talk in blocks that have some functionality that is higher than just the gates. So let's spice things a little bit, okay? Here we have our 4-bit adder, and you can see that it has two inputs, one output, but each one is a multi-bit input or output, which is, this is what it means. This tag here and the 4, this means that this is a 4-bit line, and this is a 4-bit line, and carry out is just a 1-bit line. And now let's assume that I have a number here, x. It is also 4 bits wide. This is also called a bus, 4 bits wide bus. This is the first thing I want to add. But then I have two other numbers, y and z. And I want to be able to choose which one is going to be added to x. So I can get a multiplexer here, which is a 4-bit multiplexer, basically 4 multiplexers in a row, but you can write it like that. And the select line. And the select line will help us determine which number is being added. And remember, this is hardware. If you want the option to add this line to that line or this line to that line, then everything has to be physically connected. And during runtime, we're going to select which one is going to be added to X. Okay, now a question. What happens if we have all those wonderful gates and blocks, and there is an input, there are inputs, and there is an output, maybe more than one, and at some point we need the output here to be involved in that very calculation. Can we do that? A loop. The answer right now is no, because if you think about it, whenever you change something at the inputs, it's going to flow. There is a propagation delay that you don't necessarily control, and then it's going to go to the end, and immediately it will go back and start changing again. This continuously flows, and it basically never settles. So what we have seen up until now is called combinational logic. It has no notion of memory. That you cannot do loops in it for the reasons we've just saw. And in general, all changes are immediate. There is no notion of time that you can effectively control. And this is generally insufficient. So what we're going to see next is sequential logic. And you have a hint here. We are going to add a clock to the system, a periodic clock that will help us control things and overcome the problems we have just described. Okay, so what we're going to do now is to build our way from combinatorial logic to sequential logic. Hang on, it's not going to be too bad. So we start with the SR latch, which will be the foundation to sequential logic. There are other types of latches, but we will focus on an SR latch, and SR stands for set reset. So in SR latch, we can set it by setting S or reset it by setting R to 1. And we expect when it's set that Q will be 1 and Q tag will be 0 and vice versa. The SR latch is comprised of two NOR gates, and a NOR gate is a not or, meaning that if either of the inputs is 1, the result is 0. And only if 2 inputs are 0, the result is 1. So we start by setting S to 1 and reset to 0, and let's see what happens. So the lowermost NOR, we know is the output is 0 because we have one input that is 1. So no matter what happens in the other input, we know that's a 0. And if that point is 0, it means that that point is also 0 because it's the same line. Now on the uppermost NOR, we have 2 zeros, so the result is 1. And if that point is 1, this point is also 1 because it's the same wire. And what's nice here is that the lowermost NOR now stays 0, so this is a stable system. Now if we change S to be 0, what happens is that the latch retains its value. So for the first time, we have moved from combinatorial logic without the notion of memory to something that resembles memory. And this is the truth table for the SR latch. So we see that if S and R are 0, what's in the latch is what we had in the previous stage. And if we see the set and then the reset, and on the last line both are 1, and that's a forbidden state, because when we move back to 0 and 0 there is a race condition, and also because it breaks our assumption that Q and Q tag are the reverse of each other. So we move one stage forward, and instead of having the two outputs in the while, we have a D latch. Right now it's incomplete, but we connect D to both R and S, and the result of that is that now you cannot have 1 and 1 on both R and S. If you set D to 1, it means that S is 1 and R is 0, and if you set D to 0, it means that S is 0 and R is 1. The problem is now that we cannot move to the 0 and 0 state. In order to do that, I will have to intervene where those dots are located, and I will add AND gates. So now if the enable signal is 0, the AND gates are zeroing the output, and both R and S are 0. But if the enable line is 1, then D is controlling the latch, and we kind of have what we had back in the previous slide without enable. So now we have an SR latch in which we kind of mitigated the 1 and 1 problem, and we can also enable and disable. Okay, that was quite a journey. I hope you have survived it, but I'm going to be a little bit greedy, and I want one more thing. I want a signal that will help me reset the latch at any time asynchronously. So that's my reset signal. It's active low, and therefore there is a tag on it, meaning it's active when the input is 0. And I'm going to intervene at those points that are with the red dot on them, and it will allow me, I want to enable the latch and set D to 0. What I'm going to do is to do that. Okay, I've connected reset tag to the enable signal through a NOT gate and through an OR gate, and to D through an AND gate. So whenever reset is active and it's active low on 0, that's what you get. You get a 0 on the AND gate, and therefore the output of that gate is 0, and you get a 1 on the OR gate, and therefore the latch is enabled, and therefore it is being reset. Now, that might not be how they do it in the real world, but this is something that can work. I did see other implementations, but the idea here is valid. So let's see what we have now. With our D latch, we have the notion of memory. We have mitigated the immediate changes, but not fully solved it, and I'll show you shortly why. And we still have a problem with loops. And let's see why. If I have this system here, and you can see that there is a loop from the output of the latch through some combinatorial logic cloud and back into the input of the latch. And if we connect a clock to control this, and that's what we will eventually do, we'll control sequential logic with a clock, the latch will be active on the high levels. So throughout those levels here that you can see here, throughout this time here, it will be enabled, and that's a long time. So we can still have the same problem that we had before when the system doesn't settle, continues to fluctuate. We have a mitigated problem because on the lower levels, the latch is disabled, but still that's too long. Okay, so we do have control over time because we can disable the latch, but it's not good enough. So what we'll do now is to go to the next stage, and that to move to the flip-flop. So first let's agree that this is the symbol for a latch, and we will build a flip-flop like that. We'll take two latches, and we connect the clock to the first latch, and a negated clock to the second latch, and the output from the first latch to the input of the second latch. The asynchronous reset would just connect as you would have expected. And now when we connect the clock, what will happen is that the flip-flop will only be active on a low edge and not on a high or a low level. So that's a much shorter time. So if we go back to how the flip-flop was built, you can see why this is true. And this is because the first latch will be open for data when the clock is high, while the second one will be closed or disabled. And when the clock goes down, it's vice versa. So the second latch will be sampling whatever is stored in the first latch, but the first latch is now disabled. Now let's see what happens during the high level of the clock. We can see that the D input is fluctuating, and we know that whatever values is set to D will be reflected after a propagation delay on Q. The second latch, however, has its enable input on 0, and therefore it is not consuming values. Right before the negative edge, also known as a falling edge, we can see that the input has been stabilized on 1, and therefore it is consumed by the first latch and expressed on its Q output. When the edge arrives, the enable signal for the first latch is transitioning from 1 to 0, and on the second latch it is transitioning from 0 to 1. And therefore the second latch is consuming whatever is on the Q of the first latch, and that is expressed through the Q of the second latch and also of the whole flip-flop. Right after the edge, we can see that the D input continues to fluctuate, but we don't care. Since the first latch is now disabled, it will not consume new values. The second latch, on the other hand, is open for inputs, but that doesn't matter because since the first latch is disabled, its output will not change. For that reason, we do not care if the input is fluctuating on the first part of the clock period. On the second part of the clock period, again we don't care, but this time it's because the second latch is closed. So even if changes on the D input can now change the state of the first latch, it will not affect the second latch, which is now closed. And it retains the value of 1 on its Q output and therefore on the output of the entire flip-flop. When the next edge comes, we can now see that the input is stabilized on 0. Right before the second edge, we can see that a value of 0 was stabilized on the D input and therefore consumed by the first latch. And therefore now, when the edge arrives, it is being consumed by the second latch. So all the action happens around those edges. But it is very important to remember the inherent propagation delay of those latches. So for this reason, we have to stabilize the input right before the edge and also to keep it stable just a little bit after the edge. And these are called the T setup time, which is the amount of time we have to stabilize the input before the edge comes, and T hold, which is the amount of time we have to keep it stable just after the edge. We call this process sampling, and we say that the flip-flop is sampling the input on every edge. If we take a quick look at what's happening on the Q output of the flip-flop, so first let's add that missing edge just for completeness on the left. And this is the Q output of the flip-flop, and we can see that it's always sampling on the edge. First a 0, then a 1, then a 0 again, and we can see that those fluctuations here are just not sampled. And this gives the combinational logic the time to settle, and we have to make sure that it settles on time. And here we can see that the signal is abiding by the T setup and T hold rules, and therefore we have a reliable system. If you neglect T setup and T hold, you may get something called metastability. Metastability is bad and can mess up things for you very badly. It is outside of the scope of this particular video, but I do intend to address it in future videos. So what do we have now? We definitely have memory cells now, we have pretty good control over time if we abide by the T-setup and T-hold rules. And we also have loops, and let's see why. Let's look at this loop that includes a flip-flop and then logic between the Q output and the D input. Right before the edge, we have some value when we approach time t. And now when the edge comes, we have a value that has been stabilized on the input D, T setup time before this edge, and is being sampled and reflected on the Q output. And now the logic has a full clock cycle in order to stabilize. And throughout this time, the input to the combinational logic is not going to change. And therefore, we will no longer have this effect of continuously fluctuating values in the combinational logic, because at the root, the value is not changing. So no matter what we have now that is fluctuating on D, the output on Q is remaining the same until we get to the next edge, which is the edge at time t+1. And we assume that we have built the logic right, and now we have a stabilized value t+1 on D, and the value on Q is transitioning from value at time t to value at time t+1. And then we repeat again. We have another clock cycle for another stabilization of the logic. So this barrier, in a sense, that we have in the middle is solving the loop problem. And of course, you can also build a flip-flop to be positive edge triggered, not just negative edge. Okay, that's it. I hope you like what you have seen. Please hit the like button. And also, please subscribe to that channel because there are more videos about Hobbyist FPGA programming coming. See you.